this video, I'm going to describe hybridization. We will first discuss what it is, then dive into the two ways it can be modeled, and finally walk through several problems involving those methods. First of all, what is it? Well, hybridization, simply put, is a way for valence electrons in orbitals to be more energetically balanced. Just for a quick refresher, valence electrons are when you have an atom, I'm just going to call that X, and if you were to put it in a Bohr's model, which basically means drawing a bunch of circles around it, where you can fill it up with electrons. So if this atom has, let's say, 11 electrons, making it a sodium atom, it would have 2 electrons in its first shell, as that's the maximum it can hold, then 8 electrons in the next shell, and then 1 more electron in that third shell. Basically, every single shell that's not the outermost shell, which would be this shell and this shell, are considered core shells. But then the outermost shell is what's considered that valence shell. And all electrons in that outermost shell, which I made blue here, are considered valence electrons. So here you would have 1 valence electron. And when you're doing hybridization, it's only the valence electrons that actually hybridize, and all of the core electrons just stay put. So these electron balances then can be displayed in the form of diagrams to visually describe this balancing act. And when you encounter hybridization diagrams, all you'll need to know here is that there are 3 types of diagrams you will encounter: SP3, SP2, and SP. So let's start by drawing an SP3 diagram. What we first always do is just draw our atomic diagram. And remember, in electron configuration, we always start with 1s, then 2s, then 2p, and so on and so forth. But in hybridization, the only orbitals that ever get hybridized are s and p orbitals, whether that's 2s and 2p, 3s and 3p, 4s and 4p, or whatever else. So a way to simplify this would just be to write s and p like so, because it really could be anywhere. Okay, so let's do a quick redraw and just make it look a little bit prettier. Every single atomic orbital that you're going to deal with in hybridization is going to involve your s and your p, whatever that might look like. Now, if we were to convert this into a hybrid orbital energy diagram, what do you think is going to happen? Well, what we're going to do here is we are going to take our 1 part s and our 3 parts p and actually mix them up together and average their positions. So by doing that, we have our energy diagram, and we have our benchmarks for S and P, but for SP3, the average position is going to be 3/4 of the way between S and P. And the reason for that is because we have a ratio. We have 3 parts P to 1 part S. So if we were to take 3/4 of the way P out of our 4 combined total orbitals, that leaves us with 4 hybrid orbitals 3/4 of the way up to the P energy level. So now that all 4 sp3 orbitals have the same energy levels, or called degenerate energy levels for short, we're done. Now, what do we do about sp2 orbitals? Same idea. First, I'm going to draw our generic atomic energy diagram. I'm going to put S here and P up here, 1 S and 3 Ps. But like the title suggests, we're going to mix 1 part S, but with only 2 of the Ps. 1 part S with only 2 of the Ps. And if we do that, we are going to get a ratio of 1 part S to 2 part Ps. And when averaging those positions, how far up on the energy diagram do you think sp2 orbitals are going to be? Do you think that they'll be 3/4 of the way up? Or do you think they'll be a little bit lower? Well, in this case, our sp2 hybridizations are going to be 2/3 of the way up between S and P. The reason why that is true is because we're only combining 2 parts P to 1 part S. And what about for that leftover P? Well, we left it untouched, so we're going to continue to leave it untouched here. And finally, what about for sp orbitals? Again, we're going to start by drawing our generic energy diagram as always. Never changes. 1 s orbital to 3 p orbitals. But how many s orbitals and how many p orbitals do you think I should mix this time? Well, as the title suggests, we're going to mix 1 s orbital with 1 p orbital. And if we were to do this, where do you think their average position is going to be this time? This sp orbital, 1, 2, is going to be 50% of the way between s and p, 1/2 of the way between. And for these untouched p orbitals, we are going to leave them untouched. Now, here is a really good cheat hack involving bonds and hybridizations. If you deal with all single bonds, chances are you're going to use sp3 hybridization. If you have one double bond in the mix, chances are you're going to use sp2 hybridization. And finally, if you have one triple bond in the mix, chances are you're going to use sp hybridization. Don't obsess over this for now. We're just laying out some groundwork for the next part. Okay, now how did you feel about that last part? Was it all a little bit confusing or something that's not quite clicking? If I were a student, I too would be confused. And to help with that confusion, we are going to run through a few quick examples. And by doing that, that will actually help cement the ideas that I mentioned earlier more permanently into your mind. So starting with the first of the 2 examples, we need to fill each diagram with valence electrons for an sp3 hybridized oxygen atom. So let's first begin by recalling the electron configuration for oxygen. Oxygen on the periodic table has 8 electrons, which means it's going to have a 1s2, 2s2, 2p4 electron configuration. And in this first subshell, n equals 1, there are 2 core electrons involved, meaning that we will have 6 valence electrons to work with in our n equals 2 subshell. That's because n equals 2 can only hold up to 8 electrons. So if we have 6, that means that we are within that valence bandwidth. From there, we can then draw our energy diagram listing our atomic orbitals, 1s, 2s, and 2p. But remember, because hybridization only involves s and p orbitals, and because the 2s and 2p electrons are involved in the valence shell, we can disregard 1s completely. So if I were to do a really quick redraw, where I'll just move this to the side, and I redrew our energy diagram to be our just more generic S and P energy diagram with 1 orbital for the S subshell and 3 orbitals for the P subshell. This is our new generic atomic orbital. And from there, we're then going to draw our hybrid model. So remember, because the problem asked for sp3 hybridized orbitals, we need to mix all 4 orbitals and average their positions. Hence, if we have 1 part s and 3 parts p, the average position of all 4 models, again, is going to be 75% of the way between s and p. Finally, what we can do from here is fill the diagrams with the valence electrons found in the oxygen atom. And for a fun fact, oxygen and everything below it in the periodic table in that same column as oxygen all has 6 valence electrons. So we will fill in those 6 valence electrons, starting with our atomic model, and then in our hybrid model. Of course, following Hund's rule. Okay, I want you to notice these two things. First of all, two of these sp3 orbitals are completely filled, and the other two sp3 orbitals are half filled. What do you think those mean? Well, completely filled hybrid orbitals signify lone pairs, while half-filled hybrid orbitals signify single bonds. Therefore, if we were to draw our atom, oxygen atom, we would have two single bonds on either side of it and two lone pairs. And we can confirm this by counting the number of things on the atom. Here we have 1, 2, 3, 4 things on the atom. And if we have 4 things on the atom, that always means that our hybridization is sp3. Now, for our second example, we are dealing with an sp2 hybridized oxygen. That means that rather than having 4 hybrid orbitals at the same energy level, we will now only have 3, according to this pre-drawn structure for you. And this 4th orbital is simply your untouched p orbital, and that will actually have a very special use in just a little bit. But first, we will begin again by recalling that the electron configuration for oxygen is 1s2, 2s2, 2p4, and that the 2s2 and 2p4 are the electrons involved in that valence shell, so we can once again disregard 1s, leaving us with that same energy diagram. Looks the same in slide 3. Finally, we will draw in those 6 valence electrons for both the atomic energy diagrams and the hybrid energy diagrams. But watch out for 1 second. Right before working through the examples, I mentioned that sp2 orbitals tend to have one double bond. If we draw in 1 electron in the p orbital, that tells the reader that 1 double bond exists. Therefore, I'm going to pre-draw that last electron in the p orbital. We will then draw in the rest of our 5, and this leaves one of the sp2 orbitals only half filled. Fully filled hybrid orbitals signify lone pairs, but half-filled hybrid orbitals are considered single bonds, or sigma bonds for short. And 1 half-filled untouched p orbital signifies a double bond. We can also call this a pi bond. Hence, if we were to draw out our oxygen atom, we would get an atom with 2 lone pairs, 1 single bond, and 1 extra bond. And that 1 extra bond is called the pi bond. More on that later though. So to confirm that this correlates to sp2 hybridization, we can just count the things surrounding the oxygen atom, 1, 2, 3, and subtract 1, leading to sp2 hybridization. Okay, so how are we feeling now? Do you need a quick pee break, a sip of water, a quick snack? Go ahead and take care of yourself, come right back, and we are going to cover a few more bases. But now, everything is gonna be about 10,000 times easier. Take out your notebook, we have some notes to take. As I alluded to in my last couple of examples, I mentioned the terms sigma bonds and pi bonds. And let's get into that a little bit further. Sigma bonds, simply put, are all single bonds. If I drew a methane molecule, which is CH4, all the bonds would be single bonds. Hence, they would be considered sigma bonds. Pi bonds, however, are all the extra bonds you see if you were to encounter any double or triple bond. So, for example, if you have a double bond, then one of the 2 bonds is a sigma bond, but the other one is a pi bond. And if you have a triple bond, one of the 3 bonds is a sigma bond, but the other 2 are the pi bonds. So if I drew a double bond, doubly bonded to this oxygen molecule with the lone pairs and all that, one of the bonds would be considered a sigma bond, but the extra bond that makes it double here in blue is what's considered that pi bond. And then if I drew a nitrogen molecule connected to 3 bonds, then one of the bonds would be considered your sigma bond in white, but then the other 2 extra bonds, making it non-single, are considered pi bonds. So if we were to take a look at a molecule like this one, how many sigma bonds and how many pi bonds would there be? take a moment to pause the video and try this problem out on your own. Welcome back. When solving this problem, what I find to be easiest is to actually start by counting the pi bonds, and then whatever extra bonds there are left over are just what your sigma bonds are. So first we know that pi bonds can only exist when we see double or triple bonds. So here we have one pi bond, that's what makes this bond double, and here we have two pi bonds that make this single bond into a triple bond. So there would be 3 pi bonds. Now, for sigma bonds, those are just all the bonds that are still in white. So we would have 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. I do have one last content topic that I wanted to show you, which again, we did go over a bit earlier in the video. But here are the term things that I mentioned in my last couple of examples, and now want to fully solidify what this really is. I want you to take a moment to pause the video and write my notes down in your own personal notebook, but what I want you to recognize for now is that when you have two things, you always have sp hybridization. When you have 3 things, you always have sp2 hybridization. And when you have 4 things, you always have sp3 hybridization. Now, here's a neat chart of fast facts that solidified everything that we just talked about. Take a moment to pause the video and take a screenshot. One more thing too is that unless you are learning about VSEPR, which you might not be, you don't need to know this exact part of the column. But if you do know about VSEPR, then this column will be helpful for you. Okay, so congrats on making it through all of the content. Now I'm just going to solve through some sample problems to put this into practice. The first 5 will be diagram problems, and the last 2 will be things problems. First one, fill each diagram for an sp3 carbon. Okay, so carbon is number 6 on the periodic table. So if we were to draw a quick Bohr model, we would have 2 core electrons and 4 valence electrons. Hence, I'm going to draw in 4 valence electrons right here, and then draw in 4 valence electrons right here. Because they're all half filled, these each correspond to a single bond, or in other words, a sigma bond. There are 4 sigma bonds, and the molecule would look something along the lines of this. The second problem now says to fill each diagram for an sp2 carbon. Now, remember, when we have sp2 hybridized molecules, that means that we're going to have a double bond. So right off the bat, I'm just going to put in 1 electron in that p orbital to be half filled, and that is going to signal our pi bond. And pi bonds are what makes single bonds into double or triple bonds. Because we have just one of these p's, that means that we're going to have 1 pi bond making our single bond into a double bond. Okay, now, again, carbon has 4 valence electrons, so we are going to fill in those 4. But here, one of the 4 is already occupied in that p orbital. So I am going to fill in 3 like this. Hence, when we draw an sp2 carbon, we are going to have a carbon, a double bond, and then 2 more sigma bonds. These are our sigma bonds, and if I were to put them in blue, they would be this one, and this one. And then our yellow pi bond would be this one. So, sigma bonds, 3, pi bonds, 1. And this would be what your carbon sp2 would look like. Okay, this one is asking us to fill the diagram for an sp carbon. And when we have SPs, that means that we're going to have a triple bond or 3 total bonds, one of which being sigma, the other 2 being pi bonds. 2 pi bonds means that we have 2 electrons each in these p orbitals like so. And carbon again has 4 valence electrons, so we're going to draw in our 1, 2, 3, 4, and then our 1, 2 here. This here tells us that we have 2 pi bonds, and 2 sigma bonds. And if we were to draw this out, we would have a carbon, triple bonded, and then 1 more bond here. If we were to put sigma in blue, we would have 1, 2 sigma bonds, and then our pi bonds in yellow would be our 1, 2 pi bonds. Our fourth problem is now asking us to fill the diagram for an sp3 oxygen. So again, if we were to draw our Bohr's model, 1, 2 core electrons and 6 valence electrons, because oxygen has 8 total. So our electron configuration would be 1s2, 2s2, 2p4. Only this part, the 2s2, 2p4, counts, leaving us with just 6 valence electrons. So 1, 2, 3, 4, 5, 6 valence electrons. And we would put 1, 2, 3, 4, 5, 6 valence electrons here. We remember that fully filled hybrid orbitals are lone pairs, and half-filled hybrid orbitals are sigma bonds. So we would have 2 sigma bonds and 2 sets of lone pairs. Drawing out our oxygen atom, we would have oxygen, 2 sigma bonds, and 2 lone pairs. 1 lone pair here, 1 lone pair here. And that's what your molecule would look like. For our last diagram sample problem, we are now going to fill each diagram for an sp2 oxygen. So, same as the last problem, we have our electron configuration again of 1s2, 2s2, 2p4, and only this is what we care about. So 6 totals valence electrons, we're going to draw our 1, 2, 3, 4, 5, 6. But we remember that sp2 means that we have a double bond, meaning that we're going to have 1 pi bond that makes our single bond into that double bond. So if 1 electron is already hanging out in the p orbital, we're only going to have space to put in 5 in the sp2 slots. So 1, 2, 3, 4, 5. These fully filled ones, again, are lone pairs. This one here is your sigma bond, and this one here is your pi bond. So if we were to draw out our molecule, we would have our oxygen, our sigma bond here, our pi bond here, and then our 2 lone pairs to fulfill that octet. We would have our 1 sigma bond, our 1 pi bond, and our 2 lone pairs. Okay, we are now done with our diagram problems. Woohoo! Thank you very much. Now we are on to the things. But in order to solve this problem, to label the hybridizations of each atom, we actually need to finish our structure. While this is an acceptable structure, what it's actually saying is that there are a few implications that are not directly drawn in, and I want to point those out for you now. First and foremost, all corners and vertices are carbon atoms. So we are going to draw those in, and then if a carbon atom is not already bonded to 4 unique things, its 4th thing that it's going to be bonded to is a hydrogen atom so that it gets its octet. So we have carbon here, carbon here, carbon, 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 carbon. And now this carbon, it has 4 bonds, 1, 2, 3, 4, but this carbon only has 1 bond. So I'm going to fill in 3 hydrogens because that is implied, but just not directly drawn in. This carbon here, again, only directly implied to be bonded to 1 thing, but in reality, it is bonded to our 4. So it has our hydrogens here. This one has our 1, 2, 3, but again, to fulfill its octet, it's going to have a hydrogen. This carbon is already perfectly bonded to 1, 2, 3, 4 things, so we're good. As is this one, 1, 2, 3, 4. This carbon, on the other hand, is only bonded to 1 thing, so let's draw in the rest of the bonds. This carbon already directly bonded to 4 things, and I think that's all the carbons. So we're good there. The next thing we need to do is draw in lone pairs. So on the periodic table, oxygen is group 16, so it likes to have 2 lone pairs. Nitrogen is 1 group to the left, meaning that it only likes to have 1 lone pair. And that's it. We're done. Now we can label the hybridizations around each atom. Starting with atom A, this carbon one, it's connected to 1, 2, 3 things, meaning that it is going to have an sp2 hybridization. Atom B, this oxygen, again, it's connected to 1, 2, 3 things, so it's also going to have an sp2 hybridization. This carbon atom here is connected to 1, 2, 3, 4 things, so it is going to have an sp3 hybridization. Cool. I'm going to erase these marks because we will now count the number of sigma bonds and pi bonds. So again, as always, I always start by noting which bonds have the doubles and the triples. So there is one extra bond here, one extra bond here, one extra bond here, and one extra bond here, meaning that we have 4 pi bonds, and all the rest are sigma bonds. So I'm just going to count how many extra the rest of them are. And oops, I forgot a lone pair there. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 sigma bonds. So that is that problem for you right there. Okay, we have reached our last problem, thank goodness. And the first thing we need to do is complete the Lewis structure. What we always start with is we lone pair our non-carbon atoms if they need them. In this case, nitrogen likes to have 3 bonds and 1 lone pair, so we're going to add that in. Then we need to label our hidden carbons. All corners and vertices are carbons, so we have 1 here, 1 here, and 1 here. From there, what we are going to do is add in any hydrogen bonds to carbons that don't already have 4 bonds. So with this carbon, it has 1, 2, 3, 4 bonds, so we're already good there. For this carbon, it has 1, 2, 3 bonds, so we're going to add in 1 hydrogen to make it have its 4. And then for this carbon, it has 1, 2 bonds, so we're going to add in 2 hydrogen atoms to give it its octet. Now we can count the things. For nitrogen, there are 1, 2 things, so it's going to have sp hybridization. For this carbon atom right here, it has 1, 2, 3 things, so it is going to have sp2 hybridization. And then for this carbon here, it has 1, 2, 3 things as well, so it is also going to have sp2 hybridization. Now, to make a little bit of space for the second part of the problem, I'm going to erase our markings so that we can count the number of sigma bonds and pi bonds. As always, I like to start by counting the pi bonds, the number of extra bonds that make a bond no longer single. So here we have 1 pi bond, and then here we have 2 more pi bonds, giving us a total of 3 pi bonds. And then for sigma bonds, those are all the rest. So we have 1, 2, 3 sigma bonds as well. Oh, am I stupid? Don't forget the hydrogens. 4, 5, 6. 6 sigma bonds. All right, so that's it. How do you feel? Do you feel good? Do you feel like you crushed it? Do you think you need a little more practice? Are those pesky diagrams still not making that much sense? Write a comment in the comment box. I'll answer your question. Good luck with your exams. You're going to crush it.